Hi, this will be the second set of examples for Chapter 10. This time we're going to look at some examples involving the continuity equation for flow rate and also Bernoulli's equation for fluids. You might note that we're not going to do like the last 4 or 5 sections in this chapter just because they're not on the AP exam. If we have extra time, I think we should maybe look at viscosity, which is, I think they mentioned it early in our chapter, which has to do with like the friction of fluids flowing through each other. So I think we should look at that if we have time, but we'll just see what happens. Okay, so the first example, it has to do with blood flow. It says, in humans, blood flows from the heart into the aorta, from which it passes into the major arteries, and those branch into small arteries and into lots of tiny capillaries, eventually in your fingers and all the way through your body in really small capillaries. And then they give us some information. So I went ahead and organized that. Notice, when you have a lot of information, like in some of these problems of this chapter, I like to organize them as given pieces of information. And I convert them right away. So let's see. They said the radius of the aorta, which is the first thing we're going to consider, is 1.2 centimeters. So, I better change that into meters. So let's say that's 1.2. Order of magnitude there is 10 to the negative second meters. Okay, the velocity was 40 centimeters per second, so once again we better put isn't that 0.40 meters per second, or you could use a power of 10 like I did above, it's up to you. Radius, the second one, once again we've got centimeters, so we better say that's 4, not times 10 to the negative fourth, but if we want it in meters, it better be negative sixth meters. Okay, and the second velocity is in meters per second, so we're good. Now remember, the thing we're supposed to do here, the thing they ask us is estimate the number of capillaries there are in the body. We're not going to use the continuity equation, this guy right here, to figure out one of the A's or V's. We're going to use it to estimate the total number of capillaries. So the way you want to think about this is the first thing is just the aorta, the fluid situation you have at the aorta. The second thing is not just the fluid situation you have at one of the capillaries, but at all of them all at the same time. So for A2, instead of just putting pi r squared for like the circular cross section of one capillary, you're going to multiply that by n and assume all the capillaries are about the same size. And then if you solve for n, you get how many capillaries there are. So remember, this over here represents the fluidic situation. I don't know if I'm saying that right, but in all of the capillaries at the same time. And that's why we have n. So this is one capillary times how many there are. So then you just divide that whole thing over, solve for n, and you've got it. I think it's a really neat problem. So just plug in your numbers. So I guess v1 pi r1 squared, so v1 is 0.40. Then we've got pi r1 was 1.2 times 10 to the negative second. And we got to square that, so what is that? I'm going to erase. 10 to the negative second squared. Multiply those exponents and you get negative 4, right? So negative 4. Or put squared in your calculator, no big deal. And then on the bottom, we've got, v2, which was 5 times 10 to the negative fourth. See how nice it is if you have all those units resolved at the very beginning of the problem into standard SI units. It's so much easier. And then we have, oh, the pi's cancel out, don't they? I guess I'll put mine in there, but you didn't even have to do that. So then we got a pi and 4 times 10, and since we squared it, negative 6 becomes negative 12. However you want to enter that in your calculator. So you get the number of capillaries in the body. I guess I should put an approximately equal. This is just an estimate because we made some assumptions. Remember, like the fact that they're all the same size. There's about that many capillaries. What is that, 7 billion? A lot of capillaries. That makes sense, though, because there's lots of little teeny, tiny, tiny things. Okay, let's look at another problem. I liked that one. This one says we've got a heating duct and it's entering a room. The room is 300 cubic meters in volume. Air is entering the room at 3 meters per second through the duct, and it takes 15 minutes to replenish air in the room, or if you want the air in the room to replenish every 15 minutes, how big do you have to make that duct? What's the surface area of that duct that you've got to stick in the wall? So that's our question. What's the surface area in that duct? So I just wrote down the continuity equation and said, well, okay, I'm solving for A1. And then I looked at my given information. This time I didn't write it down. Maybe I should have. But notice they gave me a volume. I don't see a volume. These V's mean velocity. That's a problem. I've got the other velocity, but I don't have a surface area either. But if I have an area, if I have a volume, excuse me, and they give me an area, there's probably some piece of information that can help me. And I think that piece of information here is the 15 minutes. So I would write this down first and then try to figure out what you need. So obviously we've got the V1 already. That's this. But what are the other things? Okay, so I said, you know what, let's just think about how we can get volume and area to interact. And I said, I think that distance equals rate times time. And if you have that, remember, rate is a velocity, so you could put our V2 in there. We don't have. So if you divide, you get velocity equals distance over time. I made distance be a length, L2, no big deal. And then what about if you think about like this? Area times length is volume. That gives us our volume that we need. So if we do area times length, we get what we need. Remember, over here what we need on top is area times velocity. So I've got area, and then we said this was equal to our velocity. And then if you look at the top, area times length is volume. And then you put a time on the bottom. So in other words, we can substitute that A2, V2 quantity to become volume divided by time. So this guy right here is what we had up there, and then we still got our velocity underneath. Now, do we have those things? Yes, I think we do. The volume was 300 meters, so you put a 300 in there. The first velocity was 3 meters per second coming out of that duct, and the time was a 15-minute time. So we should go 15 times, how many seconds is that? Times 60. Get a quick calculator. Yeah, that's 900 seconds. You wouldn't want to put 15 in there because that's in minutes. And you get about 0.11. That's area, so meters squared, or you can put your units in and see that. So there you go. That's this cross section. We don't know what shape it has. I guess if you wanted to, like the book says, if you wanted a square cross section, you'd square root that. So the length on each side, then like S. If you had a square duct that went like this, S, S, then you'd square root that. And you'd get about 0.33 meters, that's 33 centimeters. It could be some kind of rectangle though. It's up to you. They really only asked for that. Okay, let's look at one final example. This time it says we've got a typical piping system coming into a house and it's going up. So remember the Bernoulli's equation video that lady had online. I hope you watched it. Remember it had a pipe situation that looked kind of like this, where it went up into a house. Here you've got your house. Here's maybe the street, and the pipe's going up and doing some elevation gain, I should say. So in that problem, in the book, they had a lot of information. So once again, I started by just writing what they gave me. They gave me the velocity coming in at the beginning of the pipe, the radius at the beginning of the pipe, and the pressure. They also gave me the radius at the house, so it looks like it becomes thinner. And it says it goes 5 meters change in elevation to get up to the house from the street. That makes sense. And then they said, what's the velocity when it gets to the house, and what's the pressure at the house? Okay? Okay, so since you can see that the pipe has narrowed, so the stuff that we've learned should tell you that the velocity has increased, so this number should be bigger than 0.5 meters per second. The pressure should be decreased. We also learned in our reading guide and so forth. So we should get a smaller number than 3 atmospheres for the pressure. What I didn't do here is leave myself room, darn it, to convert these right away. So let's just do it on the left. 2 centimeters. Once again, what should we put in there? I think we should go 2 times 10 to the negative second, should we? Or you could just write it like this if you don't want to do that. You could go 0.02, and we should put for our significant figures another 0 meters, or times 10 to the negative second, your call. The same thing down here, that's 0.013 meters. That's already in meters. Atmospheres, remember pressure units, there's always a ton of them. There's that torr, the atmosphere, there's the SI units. We need to get it into SI units. So the conversion factor between atmospheres and, Newton meters squared, which is the SI units for pressure. You take that, let's see, where's my conversion? I'm going to have to look it up here. Atmospheres. I think it's on page 261. It says 1 atmosphere equals 1.013, so I'll take 1.013 and multiply by 3 for 3 atmospheres. And if I do significant figures, that gives me 3.0. And it's times 10 to the 5th. And remember that unit is Newton meters squared. Force per area, that's a pressure, that makes sense. Okay, we've got all that worked out. Now we've got to find 2 things. So once again, I used my continuity equation to try to find the first one. I just solved for velocity 2, and I think that should be pretty simple. So let's plug in some stuff there. So the area of the first one is going to be just pi r squared. So pi r1 squared is 0.020 squared. That's a pi, excuse my sloppiness. And then the velocity was 0.5. And the second area is going to be pi 0.013 squared. And there we go. So we get, when we do significant figures, 1.2 meters per second. There's one of our answers. Yeah, so at the house, that's how fast the water is moving. Does that make sense with what we've learned about fluids and pressure and so forth? Yes, the pipe is narrower, so we've got an increased velocity from 0.5. That makes sense. Okay, so now we're going to use Bernoulli's equation, which is a little bit long. I've reduced it here to solve for my second pressure. Remember, you start out with, maybe I should even just write it down. You start out with a big long thing. You get P1 plus, then you've got this density term, half rho velocity 1 squared, and then you've got another density term, rho gravitational constant y at that level, and then it's supposed to be equal to the pressure at the second height, which is this. Remember, those are rhos and not p's. Anyway, so notice, I wanted to solve for my pressure at the house, which is the second pressure. So I just subtracted all this stuff over, and I combined some like terms. So notice this and this are pretty much the same thing. You can factor out a half rho. So I factored out a half rho, and then I have v1 squared, subtract minus v2 squared. Same thing. These guys are just like terms as well. Factor out a rho and a g, and you get y1 minus y2. So that's why I got that stuff if you're having trouble there. Anyway, then I think we have all of our units up here, so we just plug in. I'm a little sloppy on this one, but so the first pressure we said 3 atmospheres, or 3.0 times 10 to the 5th, plus then we had a half. What was our rho here? What rho should we use? What kind of fluid are we using? Well, it's water, so we should use water, which has a specific gravity of 1. Or if we use SI units, which we have to, then we get 1.0 times 10 to the third. Remember, we're not looking at the specific gravity, we're looking at density, rho for water. And then our velocities, what do we got? We got 0.5 squared, that's 0.25. We could put that minus, what's the second one? Oh yeah, we found it, 1.2 squared. And then finally plus rho again, so we've got 1.0. Getting slop here, slow down. It's 10 to the third, and then the change in height was 5 meters. That should be our answer. So we get 2.5 times 10 to the fifth, and that's a pressure, so it's in newtons per meter squared. If you want to think about that, that's about 2.5 atmospheres, which is a smaller pressure than we started with, which is what we were looking for, so we should be good. Okay, if we have time when we get to this in class, we'll try to do some viscosity a little more, but see you later.